Yeah, good morning everyone and welcome back. You are still coming in. So let me start with a quick recap of what we did yesterday, or what we ended with yesterday. So we looked at the different types of topologies, or locally convex topologies on the bounded operators. We know we have the norm topology that is always there, that comes from the operator norm that we have. That gives us a C-star algebra. And when we wanted to look at more general types of topologies, and we came up with, for example, the weak operator topology and the strong operator topology, and they are like weaker than the norm topology. So if I close with respect to these things, I get something bigger typically. And then we introduced von Neumann algebras as algebras which are closed with respect to the weak or the strong, or actually any of these topologies that we introduced. And we found something very nice, that actually the weak closure is the same as taking the bicommutant. You take the commutant, or the operators that commute with your algebra, and you take the commutant of the commutant, that gives you the bicommutant, and that is automatically a von Neumann algebra. And so whenever you have an algebra M, such that this is the case, then M is automatically a von Neumann algebra. It's automatically closed in this weak operator topology. All right, then we looked at projections in a von Neumann algebra. So this is now a subalgebra of all the bounded operators. And we fixed such a von Neumann algebra, and we looked at different types of projections and equivalence between projections. And then, based on this idea of projections, we divided von Neumann algebras into 3 types. Or here actually there are 4 types, but so let's say 3 types. So we have type 1 algebras, so that is where you have, so in every central element there's a subprojection such that this is commutative. So the center, just to remind you, was defined in this way. And we looked at a number of examples, such as V of H, or if H is finite dimensional, this is just the matrix algebra, D by D matrices. So in this case, the Hilbert space is CD. And we found that in this case, the center is just the complex numbers, and such a thing is called a factor. When the center is trivial, then this is called a factor. And we also found another example, which is sort of the opposite. So this is a commutative algebra. These things are not commutative. Elements in here don't commute with each other. But here we have the L infinity functions, essentially bounded functions on your measure space X, and they commute with each other, like pointwise. So you take the product of 2 functions pointwise, and that commute with each other. And then if you look at the commutant of this inside the big Hilbert space, it's this one again. And so the center of this von Neumann algebra is the von Neumann algebra itself. So it has a very, very big center, the complete opposite of this one, which has just a one-dimensional center. And then we looked at, tried to identify the types. And we found, so let's say for this one, for example, you can take any projection in here, and since this one is already commutative, then if you sandwich it between 2 projections, it will automatically be commutative. And so this is automatically type 1. For these 2, we have to look first at the center, but the center is just, so any non-trivial projection in the center is just the unit operator. And so this little z here will have to be the unit operator. And then we look at a subprojection P of the unit operator, such that this is commutative, and we found that we can take a rank 1 projection. So a projection onto a one-dimensional subspace of this Hilbert space, and that gives me, and this way, so if we take this projection, then B, this will just be like multiples of this one-dimensional projection, and that's clearly a commutative algebra. Okay, so I'll show that as these are of type 1. So we haven't seen anything of type 2 and type 3 so far. And we've seen these examples. These are the most natural examples that come into mind, and they happen to be of type 1. So it's more complicated to get something of type 2 or type 3. All right, maybe just as a quick exercise, yeah. So if we want to, we looked at different types of projections. So we said projection could be finite or could be infinite, because here we have this word finite, finite, infinite. So what was the meaning of that? So we said a projection is projection P is finite if for some other projection Q, which is equivalent, for some other projection Q, which is equivalent to P and less than or equal to P, if this implies Q equals P. So if P has this property that for any other projection Q, which is this, implies this, then P is called finite. And so if we look at projections in the bounded operators, well, let's look at this one first. So let's look at this one first here. So we take a projection in here. So this is a d-dimensional space. So a projection would be a projection onto some subspace of dimension less than d. And then I take a subprojection of that, say a projection of rank n. And so I take a subprojection, Q. Since it's a subprojection, it must project onto a subspace, so rank less than or equal to n. And it should also be equivalent. And we can show that for finite rank projections, this equivalent means P has got the same dimension as this one. And so that automatically implies that it has to be the same projection. So here, everything is finite. Every projection is finite. Here, one can do a similar argument. So if we take a finite rank projection, then we have the same argument as here. If we take an infinite rank projection, then Q could be a subprojection of this infinite rank projection, which is infinite rank or finite rank. Right, but since we want equivalence, it will have to be infinite rank, and so that could be either infinite or finite. So in V of H, we've got finite and infinite projections, and the finite projections are just the ones that have got finite rank, and the infinite projections are the ones that have got infinite rank. So in V of H, this finite and infinite about projections is actually the same as saying as the rank of the projections. But we will see that in other contexts, in other types of algebras, this is not the same. You could have finite projections which actually have got infinite rank in the Hilbert space. So that's why I have to be careful about this word. But I think the basic idea of calling them finite or infinite comes from looking at V of H, which is our prototype for Neumann algebra. And so here, finite and infinite is the same as finite rank and infinite rank. Okay, and all infinite projections in here are equivalent to each other. For finite projections, they are equivalent if they have the same finite rank.
Sorry, can you explain for these infinite ones in V of H? So let's say I have a projection with infinite rank. How will this fail? Can you explain? So this should fail, right? Because you said it won't be finite.
So, okay, let's say P.
However, you're saying for any infinite projection, this will fail. For some.
P is of
Q?
So P is of infinite rank, and you suppose that Q is some other projection which is equivalent to P, so it should also have infinite rank. Q has also got infinite rank, and now Q should be a subprojection as well. I want to show that this is not necessarily true. That's right.
Oh, you just need to pick Q, right? Here.
So I can just find some example of Q
right.
such that this is true, but this is not true. For example, so if you want an example, take 1, so the projection onto the whole Hilbert space, and then take a subspace which is still infinite dimensional.
So 1 is your P, right? Right.
Yeah.
And then you could take that projection on odd or even in the sense or something.
You take another subspace, and you can then find a an isometry that maps the subspace. So we don't need one. Let's take P. So we find an isometry that maps this infinite dimensional subspace onto this infinite dimensional subspace. Okay? You can easily construct such an isometry. For example, take like here a basis in here, and here you take an orthonormal basis, and then you match these basis vectors. This is countable, so the first one here to the first one here, second to the second here, and you can construct such an isometry between these two. And that will show that, so if these two are, if you have an isometry between these two, let's call it V, then that would mean that P equals D star D, and Q would be D star, which is the equivalence between the two Q, but they are not the same. Yeah? Sorry if this is confusing. Is it okay?
I asked a different question. Do you remember the squiggly list that we did yesterday?
Sub-equivalent or something?
Yeah.
Sub-equivalent, yeah?
Did we? Not the usual one, but with this equivalence relation.
Yes. So this is the usual. This is the proper less than or equal to, and then there's this sub-equivalent, which.
Have you used that to define it?
No, I don't think we have actually used it. No. At this point we haven't. And we might be able not to use it. So this is more important. Anything else? Okay. So here we have the types of projections. And yeah, so maybe some notion. So what is particular about type 3 is there are no finite projections in here at all. And one sometimes calls these two semi-finite. And this is here then the purely infinite part. And if you start with a von Neumann algebra, any von Neumann algebra, it might not fall into any of these categories, but you can decompose it in a unique way. So if you start with some von Neumann algebra, then you can decompose it into a part that is of type 1, a part that is of type 2,1, and a part which is of type 2,3. Okay, one can always decompose that, and for any von Neumann algebra. However, if M is a factor, so if the center of M is just complex numbers, M is factor, then M has got a unique type. There's no mix. So we had two factors here, B of H, MD of C. These are factors, and they have got unique type 1. This one here is not a factor, it just happens to have a unique type 1, but you need not solve it.
Could you maybe say a few words about why this works as an argument?
Why it works?
Yeah.
Okay, this is an argument based on, like, you take, we take, for example, a maximal family of centrally orthogonal projections in there, and this way create something, a central projection that is maximal in this sense, and that would be the projection, for example, onto this first part. Then you remove that, and you look at type 2, and you consider another family of centrally orthogonal projections with this property, and you take them together, and so you construct one by one central projections that project onto this part, or this part, or this part, or this part. Okay? And this way you can get this basic decomposition. There's another decomposition for von Neumann algebras. So you can't always write a von Neumann algebra as direct sum of factors, but you can decompose it in some general way that is called a direct integral over factors, and that's why also factors are very important. But here for this decomposition, we just need these like 4 central projections that project onto each of these components.
I see. So if you, I mean, these are just von Neumann algebras of a well-defined type, and it sounds like it's a very sort lemma type.
Yeah, exactly.
Thanks.
All right, then let me move on.
So you were saying, like, if I get the general von Neumann algebra, then I could have infinitely many of these factors that are contained in it, like this integral case that you briefly mentioned.
Yes.
There I would have infinitely many factors.
Yes.
That go into it.
Yes.
And infinity x mu, I think, is a good example to have.
Yeah.
So this is not a factor because the center is very weak,
Mm-hmm.
but it has this complex numbers.
Yeah. So you could have like an infinite direct sum of matrix algebras, and then if you look at the center of that, that would just be something like this L infinity of the natural numbers if you put them next to each other. That would be the center. Like if you take like 2 by 2 matrix plus 2 by 2 matrices, something like that, and you look at the center, that would be something like this. Okay. So that is the idea here, and that's why factors are particularly interesting, because you can build up the rest of most other von Neumann algebras from that. And it's also easier to study factors because they have a unique type, and yeah. So what do they want to do? What we need now is the following thing. So yesterday in Gemma's talk, we looked at states on matrix algebras, and there were pure states and mixed states. And if you start, so a pure state can also be written as a mixed state, special case, but a mixed state is not a pure state. There's a procedure that is called purification that we mentioned yesterday that embeds the algebra, the matrix algebra, into a bigger space, and this way you can get a pure state on that bigger space. So that was called purification. And this method works in general for von Neumann algebra, actually even for C-star algebras, but that's not what we need today. And that's called the Gelfand-Naiman-Siegel construction. And so let's start with a von Neumann algebra M and a faithful, yeah, let's say it should be faithful. Actually, I haven't introduced these two words. I don't want to. So
I don't know what normal means.
it's normal, yeah. So yeah, so faithful means, let's do that. So faithful means if this must be greater than 0 for every x which is greater than 0. So for every positive non-zero x, this should be greater than 0. That is what faithfulness means for state. And this means it is continuous with respect to this. You remember this, we had these topologies yesterday. If we take the sigma weak topology, then if it's continuous with respect to this one, then it's called normal. So actually, I didn't say that yesterday, maybe I should have actually. So if you go to finite dimensional algebras, then all these topologies, they are the same. They are the same as the norm topology. There's no difference between von Neumann algebras and C-star algebras or anything in finite dimensions. Only in infinite dimensions we notice the differences. And so also if you look at states that you have on von Neumann, on finite matrix algebras, they are automatically always normal. They might not be faithful, but they are always normal. So this is fulfilled in the assumptions that we know. And even if we go to infinite dimensions in B of H, most states that come into your mind are normal. And you can always write them in such a way. So your state phi is given by applying the matrix in B of H, the trace in B of H, to some density matrix and your element in here. So phi of x would be trace of rho x, where rho is the density matrix associated to phi. Okay? And so a density matrix would be positive normalized trace class matrix. So that's what you can do in finite dimensions, and you can do the same for B of H. So this gives you all the normal states that we want. Okay, so that's what I wanted to say here. So what do we do? How do we get this bigger space? So we introduce the following GNS triple, H phi, phi phi, phi phi. What is H phi? H phi would simply be the von Neumann algebra itself that you started with. Yeah.
But in general, no such state must exist.
Which state?
So faithful state.
Yeah, so that's where I use my assumption that we have sigma finite von Neumann algebra. So we are working on a separable Hilbert space. So you can have such a thing. So in generality, if you don't want to do that, you have to work with what's called weights. So these are like states, but they can be unbounded. But that's not what we're going to use here. But to keep things as simple as possible.
Sorry, could I clarify something I should have asked yesterday? So separable, it just means I have a countable basis? Or what?
Yes, countable Hilbert basis. Yeah.
I mean, at this point, you were excluding like B of H.
No, my H has got a countable Hilbert space basis. B of H is not a Hilbert space. It's a Hilbert space. So my H could be like L2 of R. Okay, if that's my Hilbert space, L2 of n, little L2 of n. Okay.
So on B of H with H separable, you have such a faithful normal state. It's not nice or something.
On
Wow.
okay. So I define this Hilbert space, and then we have a map from M into the bounded operators of this Hilbert space, and we need a inner product in here, and we want it to be such that this is true. Okay, so this defines us an inner product structure on this bigger space. So you have some kind of map from M into the bounded operators on this space, and it should satisfy these, and that defines you an inner product. So by definition, that is defined in this way. Okay? So I haven't specified what exactly this map is, but
this inner phi goes from M to bounded operators or to H?
To H.
no.
Should be H. Should be H.
Sorry, yeah, this goes into H. Yeah. Sorry, I haven't introduced the representation yet. This goes into H. Thank you for pointing this out. Yeah, thanks for pointing this out. Now we get the map that goes from M into B of H5. And that works as follows. So P phi of X eta of Y is defined by left multiplication. So as eta phi of X, Y. Okay? So I take something in here, eta phi Y. That's a vector in H5. And then I act with this new representation, pi phi, which is essentially just left multiplication. Okay? Sometimes one actually drops all these symbols and in order to make things more readable. Which one?
Like H5 is not a open space, it's just like unless
Where H5 is then.
Yeah. Yes, you have to close it. With respect to this inner product, yeah, that we just construct. Okay, now you can find such a construction. No, there's one thing missing. So psi phi will then be defined. So since we have a unit in here, you can just define it as this one. And this is a vector now in H5. And it's a nice vector because it is psi phi is a nice vector because it is cyclic. So if I apply M to psi phi, okay, in this representation, then I get lots of vectors, so I get a subspace. And if I take the closure, then I get the whole Hilbert space. And it is also separating. So that means if this is 0 for some x, then this implies that x equals 0. So that's a nice property of this representation. But if you just look at, so say we start with M, just the matrix algebras represented on CD, then you can easily get such a cyclic vector, but this in CD, but it will never be separating. So you can have a matrix, say 1, 0, 0, 0, and if you take a vector, then the product of the two will be 0, although neither of them is 0. So this can never be like separating. And you can't find such a separating vector in the original space. And that's why here we embed the von Neumann algebra into this bigger space where we can achieve these things. And now I mentioned the word purification that we had yesterday. So why? Well, here we start with an arbitrary state with some density matrix, so this could be a mixed state. But then we get this vector, and that makes it sort of a vector state. Why? Because now we could write So we can use this formula there. Phi of y. This would be eta phi of 1, eta phi of y, and this can be written. So eta phi of 1 was defined as psi phi, and here we have phi y of psi phi. So your original state, which was sort of a mixed state here, in this bigger space becomes a vector state. So it's pure. That's the idea behind this. And so that's exactly the same we had for matrix algebras yesterday, and that's what you can do in more general. Yeah, shall we?
Can you explain again, like, kind of the idea? I just see formulas, like I don't see any statements. Sort of. We start with this, then we can construct A, B, and C.
So we start with a von Neumann algebra and a faithful state on that von Neumann
So
algebra.
you want all those requirements of your state?
Yes. Start with a von Neumann algebra and the faithful state. It's not a huge requirement. So in finite dimension, everything is. So if it is not faithful,
You can restrict, right? Like, so it's not needed.
Yeah. You can factor out the part where it is not where it is 0, and then on the rest it is faithful.
Right.
And so this way you would get, in this case you would get a quotient here, and that will be your new Hilbert space. And on that restricted part it would then be faithful. And then you could do the same construction.
Okay, so you're saying for every phi, I can find the GNS triple such that what?
Such that.
That's the last
I just there are just a bunch of formulas. I want a
So this-
statement.
Such what's this? Yes. Yeah, it becomes a vector state. You could say that is the statement. There are different applications of this. I just want to define these things, and the main property is, yeah, you could write it. As a vector.
Can we just write the statement? Because as it's right, it's true that we have a series of comments of essentially how it is constructed. Can you just say for every phi there exists
Yes. Okay.
all of these? I think it's like
So for every von Neumann algebra M, normal state phi, we can get the GNS triple say A as above, and such that phi x star y Okay.
But so for instance, this Hilbert space, like this H sub phi that actually doesn't depend on phi, is that correct?
Well,
Did you assume faithfulness?
if it's faithful, yeah, then it doesn't depend.
Okay.
The point is that this GNS construction
Well, he
doesn't.
just wrote it that
Yeah,
let's
yeah.
go to
It's a
M bar.
completion. It's
Yeah.
a completion
But
with respect to the scalar product given by phi.
Okay,
So it's
so
not-
in the completion, it will the phi will,
Yes.
or as long as it's faithful, it's not going to change.
No, in a completion it will depend. Because the inner product that we use here depends on the so that's the inner product that we define on H, and that depends on the state phi.
Could you quickly say why we want phi to be normal?
Why we want it to be normal. Now for this part,
Just so that phi is continuous.
Because you actually need it.
no, I think in this part you might not need it, as they say, so you can do it for C-star algebras in general, so you don't have normality.
Okay, so I could amend faithful and normal and the same thing.
No,
So
faithful-
Just the definition maybe of the Hilbert space would change because you need to-
Yes.
Okay. But I mean, the triple still exists.
Yes.
But if
Sorry.
phi is normal, if phi is normal, then pi becomes continuous for all of our weak topologies.
Mm-hmm.
So the image is a polynomial algebra isomorphic.
Yes. So in all the following, we will always use faithful and normal. That's why I wanted to introduce here, so that all our states are of this type.
So, let's say you will be associated with the pure state and C matrix.
Pardon?
So, like in purification, we have a mixed state and a pure state. So, which of the two symbols can correspond to those two?
So the mixed state would be, okay, the initial state phi that you have when you for Neumann algebra, that could be a mixed state, and like purification would be the state psi phi on the bigger space.
I guess the mixed state would be given by this trace of rho, like state dependent trace. That's how, like, I mean, phi itself is not a mixed state, but you compute this function that you wrote up there, this trace of rho times x.
Yes. So okay.
And
So
rho is your mixed state.
sorry. Yeah. Some people regard this as a state. Some people regard the rho as a state.
Yeah, in quantum
I think
we
in-
call rho
in
the mixed state.
in quantum mechanics, typically rho is seen as a mixed state, and this is seen as a pure state. In mathematics, typically this is seen as the state, and not this. This is then seen as the corresponding density matrix. So it's just a sorry for the confusion about
So, the loss
of notation.
in this statement is essentially then a conservation of some observable that you computed with the mixed state or you computed with the pure state is kind of the same.
Mm-hmm. Yeah. So we could go through. So we could do this for the matrices, for example, and see what happens. So if M are the d by d matrices, so we have some mixed state rho here, and then we could try and compute these things. So maybe one thing I also said, we have A, G, and S triple, so we can construct it this way, but this is only unique up to isometry, so you could change that and get another equivalent triple. And so we can use that here in order to construct one that we like most. So let's go through this description simply. So H5 would be what in this case? This would then be the D by D matrix is. This is finite dimensional, we don't have to close anything. And this can also be seen, if you like, as a tensor product of CD by CD. Now you see this original one act on CD. So that's my original Hilbert space. Now this Hilbert space for the GNS construction of purification would then be CD tensor CD. And so here we have this map, eta phi. So that should go from MD to MD. So how do we want to choose this map? There are different ways now of doing this. Some are more convenient than others. Actually, there are different ways of seeing H5. One could see it as a matrix, or you could see it as a tensor product vector space, and that will also influence what we get here. So this form resembles most what we saw in the quantum information talk yesterday. So you have these two vector spaces, which gives you, which makes the purification essentially a bipartite system. I personally like this one more, so that's why I chose MD here. So what can we do for eta phi? Identity? You could do the identity, yes. So you can map X to X. Then what would pi phi be in this case? So remember pi phi. So first let's first introduce the inner product on H phi now. So what would be the inner product? Let's use this version here. MD to MD. What would be the inner product? What would be the inner product in this case? So we are here. So we said eta phi, we choose it as the identity map, and we have X and Y here, and that should be equal to phi of X star Y. So this should be equal to trace of your mixed, well, yeah, in this case, if it's faithful, it has to be a mixed state, and here we put X star Y. Pardon?
You need to go strictly positive.
Yes. Yeah, faithful, yeah, that means strictly positive. So that gives us the inner product. Then pi phi should be the, so what is that? It's the left multiplication. How does it act? It just acts by left multiplication. And what would psi phi be in that case? Well, if we choose this as the identity map, that must be equal to unit operator. Okay. So there are other ways. That's fine so far. That gives us a GNS triple. Okay, so the GNS triple is just, this is my new Hilbert space, this is the representation, and this is the new vector state. Sorry, you can remove. Okay, this would be the vector state. Now if you look at that in this space, you get, if you represent this in here, you would get EI tensor I, where I goes from 1 to D. Okay? This would be your vector state. Now, this is not normalized, so that's not nice. And in order to do that, one could choose a different embedding where you multiply this essentially with a density matrix. And what you get in this case, so suppose this density matrix is a diagonal matrix with positive entries on each diagonal entry. So row 1, row 2, up to row n. It's faithful, so they are all greater than 0. And in that case, you would just take row I square root here. Okay? And now you can see this is a normalized state. If we take the norm of this state, then so this is row I squared. You sum over I from 1 to D. Since it's normalized, all these row i's will sum up to 1. And that makes this a vector state of normal. And this is pure, so because it's a vector state in here. And you also see it is entangled. It's highly entangled in the sense of what we saw yesterday about entanglement. I think there will be more about entanglement today in the lecture. So this gives you an entangled state. Started, yeah. So it's a pure and entangled state on this bipartite system. That's what happens with purification. So you ask about the Bell state. That would be something new.
So is this like a maximally mixed state of just one system, but when we embed into the total system of values involved, it's a maximally entangled state?
It doesn't have to be the maximally mixed.
It doesn't have to be maximum. So maximally mixed you would get if rho has got 1 over D on all the diagonal entries. In this case, it doesn't have to be 1 over D. It could be, but it has to be non-zero on all the diagonal entries. Okay, so that shows what happens in the D by D matrices, and for other ones, it's not so nice to work out. So I think that's the best example you can imagine. Anything else about this? Shall we have a break? Who wants a break? Nobody.
But I think you have decided
No. Okay, so we have this GNS construction, purification, and what we actually wanted to do for today is to see some other types of von Neumann algebras. Okay, so let's move on. So examples of factors. Okay, so the first example that we had was these two. So I've always got these ones, a finite dimensional one and an infinite dimensional one. So provided H is infinite dimensional. So now I want to construct another factor, and so that requires some more work. I already said that the ones that are more straightforward that come into mind, unfortunately happen to be of type 1. So if we want to get something of type 2, we need to do a little bit more. Let's do a break. Okay, so let's look at this example now. We do the following. So we saw here like a tensor product of vector spaces, and in general you can construct a tensor product of two Hilbert spaces. Essentially, the same way you do take vectors from the first one and the second one, and that gives you the algebraic tensor product, and then you close it with respect to the inner product. So the inner product that we get if we have two Hilbert spaces would be the inner product on the first one times the inner product on the second Hilbert space. And that defines us an inner product on the tensor product Hilbert space H1 tensor H2. And we can do the same with 3 Hilbert spaces and in general n Hilbert spaces by just taking the inner product on each of them and taking vectors of this product form and then taking the span and the closure of that. Okay? So, problem arises if we want to go to infinity. So imagine I have got infinitely many Hilbert spaces and I want to construct a tensor product of these. So how should I do that? It's not quite straightforward. So whenever we have something infinite, we usually construct that as a limit of something finite. So we can take finitely many Hilbert spaces and tensor them, but then how would we get from there to infinity? So if you take the direct sum, that's a bit easier. I can just add further terms, but with the tensor product, that's not so clear. And so what we do is the following. So we have a n Hilbert spaces. So we have Hilbert spaces each n, and some vector psi n. So let this be a sequence of Hilbert spaces with some designated vector psi n in Hn. Okay, so Hilbert space with some vector. And then we have embeddings. So we have following. So we take the tensor product of the first, say, n minus 1 Hilbert spaces. So by this I intend like the closure of the algebraic product. So this is a new Hilbert space. And I want to embed that into the Hilbert space where I have Hn here. And so the way I'm doing this, so here we have Hn minus 1 tensor Hn. So how can I embed this? If I just attach the 0 vector, for example, in the last component, as I would do it for the direct sum, then I would get 0 here. So if I have x1 tensor x2 tensor xn minus 1, and then I tensor that by 0, because 0 is everywhere, always in H, then I get just 0. Everything you tensor with 0 becomes 0. So that's not a good choice. Is there a better choice? I can use the psi. That's the reason why it exists. So I tensor this thing with psi n on the right, and this way I get a well-defined embedding. Let's call that.
You want your vectors to be unit vectors.
Yes.
Psi n.
Yes. Designated unit vectors. Okay. So that gives me an embedding, and that I continue up to infinity. And so I can define then. So there's a bit of work. I'm going to skip this, but you can define then, using this idea, you define H as the direct limit Hilbert space of this. Okay, you intend this to infinity, and that gives you the direct limit Hilbert space. Now, if you change psi n, if you choose a different vector, then you would get a different result. So this construction depends on the choice of your psi n. Yeah. Okay.
What is a direct limit? What is the word direct mean?
So let's forget about direct. let's just call it limit. Let's call it limit Hilbert space. So you have this embedded into this one. So you get something bigger and bigger. You take the union of all of them, and then you take the closure, and you get the Hilbert space in there. Okay?
I suppose you can think about it as infinite tensor products, but all the finitely many of your vectors have to be these psi vectors.
Yes, so yeah, that is what the union is. So if you take the union of each of these spaces, you have the union of finite tensor product Hilbert spaces. So everything inside this big union is a finite product, but then you take the closure of it, and so in the limit you get infinite products as well. You can't write them down properly, they never arise, but in the limit they are there. Okay? So why do we want this? So now we do the following. So given finite dimensional Neumann algebras, the faithful state phi n for every n. Okay, so I have now this sequence of von Neumann algebras with a designated state. Okay. Then what we do is we use this construction here. So on some Hilbert spaces, and then so we consider the GNS construction for each of them. And this results in a sequence of Hilbert spaces now. So H, the first Hilbert space, is this GNS Hilbert space for Mn with the state phi n. So you see, whenever I start with a von Neumann algebra and a state, I get this Hilbert space H phi psi phi. Okay, I drop the pi for now, and that is my GNS Hilbert space. So I get a sequence of Hilbert spaces with designated vector inside the Hilbert space. Okay, so that is my H phi n. Okay, so I call H the Hilbert space that you get as the limit of this. Now, this gives me then a Hilbert space. So this is the infinite tensor product of this. So this is the Hilbert space that we have here. Sometimes one just writes that as this infinite tensor product. Okay, so what can we do with this? Well, then if you take our von Neumann algebras, they will act on this. So if you take the tensor product of von Neumann algebras, they will act on this tensor product of Hilbert spaces, because each Mn acts on its corresponding GNS Hilbert space with this representation here. So now we can take the tensor product of von Neumann algebras, and that will act on the tensor product of Hilbert spaces. Is everybody happy with that? Does it make sense? So if we take this tensor product of representations that we have here, and you take a tensor product of von Neumann algebra. So this symbol here with a circle and a little dot inside, by this I mean you take finitely many von Neumann algebras Mn and elements in those, and in all the other ones, because there are infinitely many von Neumann algebras there. So in all of them, you take just the unit element, and in finitely many, you are allowed to take something different from the unit element. Okay? So your overall infinite product will be 1, 1, 1, and then there will be something non-zero, a non-unit, so x, and then you have lots of ones again. And you've only got finitely many positions where you're allowed to take something different from 1. That is what I mean here. So it's a tensor product, but like a simplified one where only finitely many ones are non-zero. Okay? So that can be easily constructed. You don't have to do any limits, because once you have infinitely many non-zero entries, you get again into trouble with limits. So we just take the ones with finitely many non-unit factors, and all the other factors in here, this infinite product, are just the unit. So they act trivially on the Hilbert space. So if this acts on a Hilbert space now, I let this act on this big tensor product Hilbert space. Then, so there are infinitely many positions here, and at almost all of them, it just acts as the identity. It doesn't do anything. And just as at finitely many positions, it does something different from the identity. So it does something on this Hilbert product, in this tensor product. Okay, if you write it down, H1, H2, H3, and so on. Then M1 acts on this first one, M2 on the second, M3 on the third. But most of them are just the trivial actions, because you just have the unit element at most positions. So nothing happens at these. Only where you have something different from the unit, something non-trivial happens. You change that. Okay? We're happy with that? So that is how this works. Okay, so what is this thing? So we have a tensor product of von Neumann algebras. And every element in this tensor product can be written as finitely many non-unit factors, and all the other ones are units. So what type of object is this? This is again an algebra, at least, right? So when I have two elements in here, so two infinite tensor products, with most of them just unit, and another one, infinite tensor product with most entries just unit, I can just multiply them with each other component-wise. So I have, say, x1, tensor x2, tensor x3, and so on. And I multiply this by y1 together. Something unclear?
I was asking about the sums, like when you say it's an algebra, like what kind of sums am I allowed to take? If I'm allowed to take infinite sums.
No, just finite sums. So sums means one element plus another element. And then inductively you can have 10 elements and 100 elements, but never infinitely many.
But I can take limits of those things.
Limits, yeah, but not in this one.
Okay.
So this is just algebra. When we say algebra, there's no idea of limitness and yeah, closures and so on. It's just algebraic relations. So product of one times the other. Sum one plus the other. Okay? So that's what you would do about the product. You take one element in here and another element in here, and almost all of these entries are actually just the identity element, apart from finitely many. So that gives me the product. How is it defined? Well, it's defined as x1 times y1 inside the first one, tensor x2 times y2 inside my second, and so on. I get all of them. Now, if almost all of them, or but finitely many ones here and here, are just equal to the unit operator, then what happens in the product? In the product, the same will be. You might have get more that are not equal to the unit operator, but everywhere where this and this is the unit operator, you will have the unit operator here. So that will be the case for almost all of them, except for finitely many. Okay? So that's the product that I have in here. And similarly, you could consider direct sums. So sums of elements in here, inside. Okay, that's a bit more complicated, but we don't need that. We don't need sums. That's my algebraic tensor product of this. So that's very similar to what we have in, if you have just two algebras. If you take the tensor product of just two, we had, like yesterday we had the qubits, and you have the 2 by 2 matrices for one qubit and another qubit, and so the composite system would be just tensor product of the two. So you have one observable in the first qubit, one observable in the second qubit, and you take the tensor product of two. Now if you have more and more qubits and infinitely many qubits, then we'd have to construct this algebra here. Okay, because once you have infinitely many entries that are different from the unit, it becomes problematic, because you have to work with limits. All right, so that's my algebraic tensor product. We call this algebraic infinite tensor product. Okay. So we see that this algebraic tensor product of the MNs, this acts on the so that acts on this infinite tensor product Hilbert space. Okay, that you get via this limit construction here. So that means if you apply this map, phi n of so this is the map that embeds this into the space. That is a subalgebra of this infinite tensor product. Okay? That's what it means to act. So if this algebra, if this infinite tensor product acts on this big limit Hilbert space, that means, so by bounded operators, it means this becomes a subalgebra of this big infinite tensor product Hilbert space. And does it have a unit? Who thinks it has got a unit in the picture image? Okay, so what is this unit? How do we get the unit? Well, so remember this is just left multiplication by an element. So if we just take the element which is unit, tensor unit, tensor unit, tensor unit, infinitely many times, all right? And we represent that by left multiplication on this space. That's what we do with this one here. Then this just acts as the unit on this infinite tensor product Hilbert space. So it is a unital subalgebra by just taking the unit, the infinite tensor product of the unit, that acts as the unit here. And it is also a star algebra. Okay, so what could we do now if we want a von Neumann algebra? So, von Neumann, pardon? Double commutant, yeah. So, we saw yesterday that von Neumann algebra was an unital star subalgebra of B of H. So this is my H. Okay, this was H. And it's the weak operator theory closure of that. And equivalently, it's just a double commutant. So we can take the double commutant, and that gives me a von Neumann algebra. So define M as the double commutant with respect to this Hilbert space here. Okay? And this is a von Neumann algebra. Okay? Pardon? A characterization for one?
When it is a factor.
When it is a factor. Yes, so we're going to come to this one. I think I can't write below this, right? So I'm going to erase this one. Yes. I think this should be sufficient. So, yeah. So we have this M. So this M looks somehow like an infinite tensor product, but there's a lot of more information in there because the whole construction of this M here depends on the choice of these pi phi n, and pi phi depends on the choice of phi. Okay? So we can always get such a phi, but if I change phi, I will get a slightly different Hilbert space and a slightly different representation and a vector psi phi n, and hence this final thing will depend on the choice of my states. So that's important to notice. So what one can show is the following. If Mn is a factor for all n, then M is also a factor. Essentially what you do is you look at the commutants of each of these Mn's, so Mn commutant and the tensor product of those, and this way you get the commutant of this M. Okay? You have to work a bit, but what intuitively seems to be the case is actually the case. And so here comes another important thing. If phi n is a normalized trace. So phi n is a normalized trace. We would say maximally mixed state. So if you look at this row that we have, there. If we look at this row, if this is a maximally mixed state, so you have the same entries, 1 over d, 1 over d, 1 over d, on all of them. So then that's what we would call a normalized trace. So normalized trace is just a trace divided by d, so that the trace of the unit becomes 1. Normalized trace, so that's just 1 over d times the trace of md. So I said I want finite dimensional algebras, and if they are actually factors, then they are all the d by d matrices. So that's the normalized trace. So in other words, maximally mixed state in physics. Then what happens? Then you can imagine like a tensor product of all these phi n's. This is a normalized trace. So a trace is the nice property that if you have xy, the trace of xy is the same as the trace of yx. So that's trace of xy is the same as the trace of yx. That's a particular property of a trace. So finite trace. Okay, so these are two important things that one can show. So if mn, all mn's are factors, then this reciting infinite tensor product will also be a factor. So that means there's trivial center. And if these phi n's are normalized traces, so maximally mixed states, then this infinite tensor product will also be a normalized trace. Okay? So that's what we can observe. So now we have most of what we need. If we look now at these different types up there, so we have type 1, type 2, type 3, and we already saw some examples here. So these are examples of type 1 factors. So what we can do here now is we make the following choice. So far everything was very general. The question is now, what do we choose for mn and phi n? So now choose, now make things specific. So now we become specific. So we choose mn equal to the 2 by 2 matrices. Okay, just as a special example, 2 by 2 matrices for all the mn. So we have an infinite tensor product of 2 by 2 matrices. And we choose the phi n's as this maximally mixed state. So 1 over d times trace. Or in other words, so the density matrix would just be a half. Okay, so that's our choice that we make. So we do the same for all these factors that we have, tensor factors. We could do something different for each one, but we check now the same for each of them. So we just have an infinite tensor product of 2 by 2 matrices constructed in this particular way. Then, so I think I can now erase this. Then what happens with this choice? Now these ones, they are factors, right? And this one is a normalized trace. So according to these two statements here, that means that the infinite tensor product will have to be a factor and that there will be a normalized trace on this infinite tensor. So, and then M is so M is now this infinite tensor product with this choice 2 by 2 matrices. This is a factor and there is a normalized trace on M. Okay? Now the question is, what is this M? Have we ever seen this M before? Probably not, because can it be one of these over there? So can M be this one here? Why can't it be this one? Why can't it be just the D by D matrices? So think about the size of M. How big is M actually? How big is this infinite tensor product? I tensor 2 by 2 matrices infinitely many times. How many dimensions have I got? Infinitely many. So it can certainly not be any of these. Could it be this one? So what's the problem with B of H? Why can't it be all of B of H? So we have a trace. On B of H, you have a trace, but it's not finite. So if you take the trace on B of H, and you take then it's unbounded. So finite rank operators will have finite trace. So a d-dimensional projection in here will have trace D. But if you take the unit element, then that will have infinite trace. So there can't be a finite trace here. But here, there is a finite trace, namely, that's what the statement here shows. You can have a normalized trace. So normalized means that the trace, or the normalized trace of the unit element is exactly 1. So there is a normalized trace in here. So this M cannot be of type 1. So we've got our first algebra, which is not of type 1. Good question.
Yeah, can you explain again why couldn't I have a normalized trace on B of H? Like, why can't I, like...
Pardon?
I'm not a physicist.
Sure.
I don't like that.
So, yeah, the trace on B of H is just the trace that you...
Why can't there be another one?
Yeah.
Why can't there be another one? Pardon?
Projections are equivalent.
Yeah, so yeah, you have the rank 1 projections that are equivalent, and so if you sum up all the rank 1 projections, so every rank 1 projection should have the same trace because they are like equivalent. So
Right, and then I get infinity.
yeah, if you have two projections which are equivalent, then they must have the same trace, because equivalent means like one projection is this one, the other projection is this one, and so the trace of P is trace of V star V, and that's the same as V star, which is the trace of Q, right? And so if you have infinite dimensions, you sum up the same number, whatever it is for rank 1, and you get infinite times that number.
Okay, you're using also, I guess, that I can express identity as an infinite countable
Yeah.
sum over the basis.
Yes, exactly. Okay. So this is a normalized trace. So this must be something of either type 2 or type 3.
Sorry, excuse me? I mean, you convinced me that it's not VH, but why could it not be of type 1 at all? Are you saying that type 1 is only of the form VH?
No, I haven't. Yeah.
But you can just say that it's true.
Yeah, I can say it is true. Yeah. Well, that the type 1, so one can show that the type 1 factor is isomorphic to B of H, with H either finite dimensional, in which you get this MD, or infinite dimensional, in which you get the standard B of H. So whenever you get a type 1 factor, then you can, in theory, construct such an isomorphism to B of H. So that gives us like all type 1 factors. They are the yellow ones. So, yeah, so I didn't say a lot about traces, because there was not much time. But, so one can show that for type 3 factors, there are no traces at all. And for type 2 infinity factors, there are also no finite traces. But here we have a finite trace, because like the trace of the unit is 1. I said it's a normalized trace. And so that shows that this must be of type, hence M is of type 2,1. Okay? And this has a special name. This von Neumann algebra is called the hyperfinite type 2,1 factor. Okay. And one denotes this by this calligraphic R. So this has a very special meaning in von Neumann algebras. And this is also very important to the Kohn embedding problem, so that's why I wanted to include this example here. So that gives us this type 2,1 factor. So we saw that's a factor. We sort of saw that it is type 2,1. And hyperfinite, so this just means that you can approximate it by finite dimensional algebras. So that's the case because we constructed everything as the limit of a finite tensor product. So that's why it's called hyperfinite. There are other type 2,1 factors which are not constructible in this way, but this one is, and that's why we call it the hyperfinite 2,1 factor.
You get to infinity from this construction?
Pardon?
You get to infinity from this construction?
You can get to infinity. Yes, you can get to infinity. But I'm infinite tensor product. You can definitely get to infinity by taking like this construction and just tensoring everything with B of H, and that gives you.
So you really need to just take the first factor to B of H and then you do whatever you want with the rest.
Yes, but then sort of in this construction all of them were the same and I used them to be finite dimensions. So the question is, can we get them, can we get it as infinite tensor product or finite dimensional? So I'm not aware, not sure whether you can, but yeah, if you want, take material construction and just take B of H for the first one and then these M2, M2, and 2 for all the others.
If you take finite dimensional, you will have normalized trace, so you won't get between. But you can choose.
No, but I said it's not. On the first factor, you would then not be able to take the trace.
Taking the sequence.
Yeah. Any other questions?
I'm guessing if you start with any other size matrices, you still get the same factor. So in this whole construction really depends on the choice of the matrix, so the algebras that I take, the MNs, and the choice of the phi n's. Already changing the phi n a little bit can change the whole overall outcome. I think I might speak about that in the afternoon, but you can get some other things, but so it really depends. It depends a lot on the choice of the individual factors that you do and the states
that you pick
The
on
question was also if you take different size matrices but still take the normalized traces, then you do get the same.
Yeah. If you still take the normalized trace, then you get the same. Yeah. We're done, but I thought there were questions, so.
Okay,
Yeah.
let's take